x equals x0 plus v0t plus 1/2 at squared. So check it out. If you call the top 0, the top position, then this x becomes h, how high it's going to fall. And for you guys, that's going to be around 0.75 meters. It'll be around that, plus or minus a couple centimeters. And it starts from rest, so there's no initial velocity, so you have h equals 1/2 at squared. And if you solve that for a, you get 2 times h over t squared. So that's the formula that you're going to do to find the linear acceleration. Now, I'm going to want to see somewhere there a sample calculation. If I were you, I would have a calculation section where every time I'm making a calculation for this table, I do the one for the first row. That's just an easy way to keep track of it. I want to see the formula you use and what numbers you put in. So I can, if there's something goofy, I can see where you're going wrong. Okay, now alpha, that comes from, you may recall from class, A equals alpha r. That's the tangential acceleration, and that's what we want. I'll call it a sub t, maybe there. So to get alpha in radians per second squared, that's the angular acceleration now. That's going to be a divided by r, where r is the radius of the shaft. Okay? You with me? So, I guess I could be getting numbers there, but I'm not. Let's see. Tension. Okay, what do I have? Like 5 minutes?
Yeah, 10 minutes.
Oh, yay, okay. Okay, so maybe I should go ahead and, so this would be 2 times, let's say 0.75 meters divided by 24 seconds squared. That's what you're going to get in this one, and that would be your sample calculation. This number will vary, so will this one, depending on your setup. You'll get slightly different times depending on how much friction there is in the apparatus. I don't know if anybody wants to calculate that number for me, but then you take that number and you divide that by the radius of the shaft, which was 0.006375. 0.006375. So it's A divided by that. Okay, now to get the tension, we're going to look at the hanging mass that's falling. Name a force acting on the hanging mass.
Gravity.
Gravity. So you've got gravity pulling down, F sub g, which is the mass of the hanging mass times g, which is 9.8. So for this first trial, that would be, where am I? 0.05 times 9.8. That's the gravitational force pulling down. And it'll change with each mass, times 9.8, or 9.81 if you want. Okay, then what's another force acting on that hanging mass? Tension in the string, very good. So you got the tension in the string pulling up, but it's less than the force pulling down because it's accelerating downward. You know it's accelerating because this thing's spinning faster and faster the closer to the bottom it gets. So I'm just going to call that T. And the reason we need T is because T is what's causing a torque on this shaft, all right? So we've got to get T so we can get torque. So T in newtons, and let's see. Here's where we're going to do that same F net thing. F net equals MA, and F net equals the vector sum of all the forces. So the vector sum of all the forces, F net equals the big force minus the little force. Are you with me on that? And what does Newton's second law say F net equals?
MA.
MA. So we're going to equate MA to FG minus T. And if we do that and solve for T, we get T equals MA minus, FG minus MA. I did it the wrong way in my head. Okay, so this column will be generated using this formula, FG minus MA. So for the first one, it'll be 0.05 times 9.8 minus 0.05 times whatever the A was over here. Okay, and that's going to change for each row of masses that you do. Okay, now we're ready for torque. And it's in meter newtons, or some people call it Newton meters. I prefer meter newtons. And torque is equal to the radius of the shaft times the tension. That's an R. So that's just going to be the radius of the shaft times whatever the tension is that you get right there. Okay, a lot of calculating. Calculation heavy this lab. Okay, now, once you've got that table all filled out, then you're going to make a graph. And I guess I've just got room here to show you the graph. It's going to be torque versus alpha. So you've got torque in meter newtons up here, and you've got alpha in radians per second squared on the x-axis. And you should get something that looks kind of like this. I guess you'll only have 4 points, I don't know. Of course, they probably won't fall that nicely on a line. And you're going to do a best fit line. And the slope of this is going to be your measured I of the system. And we've already calculated I of the system. Oh, did anybody add this up? This is, we need that sum, I total. That's what we're going to call your calculated. This is your calculated value, and the slope of that graph is your measured value. And this is the rotational analog to Newton's second law. The torque equals I alpha. That's the relationship we're testing. Torque equals I alpha. So when you graph torque versus alpha, the slope should be I. And it should be, you're going to do a percent difference between the slope and the sum of those four inertias. Does it, I guess you guys can do that addition yourselves. Okay? All right. I don't know. The results on this are kind of iffy. I mean, you may have as high as 20% error. If you get in single-digit percent differences, wow, pat yourself on the back. Okay?